Ampere's law provides an alternative formulation of the relation between a magnetic field and its sources. In some problems it is more convenient than the law of Biot and Savart. The role of Ampere's law for magnetic fields is analogous to that of Gauss's law for electric fields, which we studied before. Recall that Gauss's law relates the integral of the normal component of electric field over a closed surface to the total electric charge enclosed by that surface. Ampere's law relates the tangential component of magnetic field at points on a closed curve to the current passing through the area bounded by that curve. Ampere's law is formulated in terms of the line integral of the magnetic field around a closed path, denoted by this equation here. This is the same sort of integral we used to define work and electric potential before. So we divide the path into infinitesimal segments, dl, and calculate the scalar product of b and dl for each segment. In general, b varies from point to point, and we must use the magnetic field b at the location of each dl. The circle on the integral sign indicates that this integral is always computed for a closed path whose beginning and end points are the same. As with Gauss's law, the path used for Ampere's law need not be the outline of any actual physical object. Usually it's purely geometric curve that we construct in order to apply Ampere's law to a specific situation. To introduce the basic idea, we consider a long straight conductor carrying a current I, and imagine a circle of radius r in a plane perpendicular to the conductor and centered on it. Then from this equation, the magnetic field has magnitude mu naught I over 2 pi r at every point on the circle, and it is a tangent to the circle at each point. So that is the line integral of the magnetic field B is equal to mu naught multiplied by the current passing through the area bounded by the circle. We can also derive this result for a more general integration path, such as the one here. At the position of the line element dl, the angle between dl and b is theta, and b dot dl equals b dot dl b dl cosine theta. From the figure, dl cosine theta equals r d theta, so we got r d theta here, so that's that distance here, where d theta is the angle subtended by dl at the position of the conductor. Thus, we can write the closed path integral of b dot dl equals a closed path integral ui 2 pi r r d theta. So we're writing this now. R d theta equals ui equals this bit here. But this integral here is just the total angle swept out by the radial line from the conductor to dl during a complete trip around the path. Well, that is 2 pi. Thus, again, we get to here. The line integral does not depend on the shape of the path or on the position of the wire within it. If the current in the wire is opposite to that shown, the integral has the opposite sign. Now suppose several long straight conductors pass through the surface bounded by the integration path. The total magnetic field at any point on the path is the vector sum of the fields produced by the individual conductors. Thus the line integral of the total magnetic field B equals u naught times the algebraic sum of the currents, with currents going into the page considered as positive and those coming out of it considered negative. In general, the positive direction for current is determined by a right-hand rule. Considering a line perpendicular to the surface, we wrap the fingers of the right hand around this line so our fingers curl around the same direction as we plan to go around the integration path. Then the thumb indicates the positive current direction. So we can work out the current direction by putting our fingers in the direction of where the magnetic field's going to go, and then as we sweep round we know our thumb then is pointing in the direction where the current's going. If the integration path does not encircle the wire, or if a wire lies outside the path, the line integral of the magnetic field B of that wire is 0, because then the angle theta does not sweep through 2 pi as it did before. Instead its net change is 0. Hence, if there are other conductors present that do not pass through a given path, they may contribute to the value of the magnetic field B at every point, but the line integrals of their fields are 0. It follows that if we interpret I in b dot dl equals ui to mean the algebraic sum of the currents through an area bounded by a closed path, this equation implies all of the above statements. Thus the general form of Ampere's law is the line integral of the magnetic field vector B around any closed path is equal to mu naught times the net current through any area bounded by the path. Although we have derived Ampere's law for the special case of the field of a number of long straight parallel conductors, it is true for conductors and paths of any shape. The general derivation is no different in principle from what we have presented, but it's more complicated geometrically. Finally, we emphasise that the statement closed path integral of B.dl equals naught does not necessarily mean that the magnetic field is naught everywhere along the path, but only that the total current through an area bounded by the path is zero.